Now, let's identify each of those process attributes and define each one of those attributes separately. So when we say a process identifier, we refer to a unique identifier that is associated with each process. And this identifier is actually used to differentiate a process from another process by giving each process a unique identifier. Another attribute that we use it to define some properties about a process is called the process state. So a process state is an attribute that is used to describe the state of a process, whether the process is in a running state, like the process is actually running right now, that means the process is under execution, or the process is ready to be executed, or the process might be even blocked. So we use this state attribute to describe the state or the status or the condition that describe a behavior of a process. It could be running state, or it could be ready state, or it could be, for example, blocked state. So another attribute that we use it to define a process is called priority attribute. This attribute is mainly related to the priority level for each process. So if we do have multiple processes, and for example, if we have process 1 and then process 2 and then process 3, process 1 is of priority 5 and process 2 is of priority 2 and process 3 is of priority 4, where we have a number to describe the priority level of a process. That means the first process that the operating system will execute it is process 1 because it has the highest priority. So an additional attribute is called a program counter, which we have known before. It's just the starting address of the next instruction in the program to be executed. We should have this because once the process is located in the main memory, we would like a pointer to point to the address where the instructions, the address of the next instruction will be retrieved for execution. Couple of other points are needed as well to be used to describe the property of a process, including those memory pointers. And those pointers, including the program code, they will point to the code of the process as well as the data associated with such a process, in addition to any memory blocks that might be shared with other processes. So in addition to some pointers that we use it to refer to either a program code or a data associated with the process, we are interested also in defining a context data. A context data is this data that we use it, and actually they are presented in the registers in the processor while the process is executing. For operating system, it's not only about monitoring the behavior of a process, it's also mandatory to monitor the behavior of the processor. So we keep some information and some data in those registers in the processor while the process is in execution. So we can actually perform some quantitative performance analysis and see the behavior of the processor. In addition to this, we do need some input-output information, and this will include any I/O request, any I/O devices, for example, like disk drives assigned to this process, and any additional list of files that they might be used by the given process. So for each process, we are storing all of those attributes, starting by the identifier, followed by the state of the process, and then a program counter, and then some memory pointers, and keep going. And we end this data structure that we use it to store all of this information about the process by accounting information. And accounting information, it might include some quantitative measures about the processor utilization, which means the amount of the processor time, how long it took for the processor to execute or to run such a process. Also, the clock time used, the starting time and the end time, and the total amount of time in a system, some upper bound and lower bound related to some time limits. So in addition to account numbers and so on. So we might even have some average delay time. So this is average delay time in a system. And in addition to the average total time in a system, this is for each process. So for each process, we need to know how long this process has been in the system before being executed or run. All of this information, ending with the accounting information, are stored in a data structure that is called process control block. So we call this a process control blocks. Sometimes we use abbreviation as process control block to identify the information that is needed to describe a process. Typically, it's a data structure that is stored in the main memory when a process is ready for execution. We know that this process control block is created by the operating system, and it's a very significant point about a process attributes or a process behavior, because it has all the information, the sufficient information that we needed to run a process. And actually, it also has all the information that we needed if a process is interrupted. So you do have a running process in place, and then the process was interrupted. So by retrieving the information from the process control block, we can actually later resume the execution as if the interruption actually has not occurred. So using all the information in the process control block, including identifier of a process, the state of the process, the priority level, the program counter, memory pointers, the context data in the processor registers, the input-output status information, as well as the account information. This is where we do have all of the information needed about the process elements inside the process control block. So the process control block is a key tool that actually enables the operating system to support multiple processes and also to provide multi-processing. As I said before, because we have all the information and the attributes related to a process, including but not limited to the identifier up to the accounting information, it's easy for the operating system to retrieve a process if a process was interrupted. And that will give a chance for the operating system to switch back and forth between processes. If one of them is interrupted and the other one is not, then the operating system schedule will jump and execute this process. And when there is a chance to resume the interrupted process, the operating system will retrieve the process control block and then will allocate the information needed to resume the process again. And by this, we support multi-processing, multi-programming environment. The program counter, so keep this in mind that the program counter, so the program counter and the context data, so some information about those registers that are stored in the registers of the processor to monitor the behavior of a processor are actually useful because we will load them and will monitor the values of the program counter, which like the first instruction to be executed for a process, as well as the register status to start executing a process as well. Thus, we can say that a process could continue a program code, associated data, and a process control block. So it's easy for us that we now identify a process which will be characterized by the process elements. Our process elements right now include the program counter and then the data associated with the process, and then the process control block. And then for a single processor computer, like if I assume for simple case, we only have one processor in our system at any given time, at most one process is executing, and the process will be in a running state by monitoring and observing the values in the process control block. So in summary, a process control block is a data structure that is really mandatory to be created by the operating system, saved in the main memory once the process is in the ready state, and used later on if you would like to resume a process that was interrupted or blocked, or even jump between different states. Keep in mind that the process control block is created and managed by the operating system. So this is one of the core data structures that we use it to monitor the behavior of the process, to execute a process, to even allow the process to enter the system. So once a process is created, so we do have a new process, immediately the operating system will create the process control block, and then all the information will be stored in such data structure. And this information will be used either to handle a new created process at this moment, or to retrieve a process when needed. So using the previous data structure actually is not enough. It might be a mandatory or like a useful task that for a given program to be executed, or a given process to be executed, or a task to be executed or created for a given program, from the processor point of view, it just executes some instructions from the beginning to the end in the sequence that it was provided, and then by simply changing the values in the program counter. And over time, the program counter may refer to code in different programs that are part of different processes. But from the point of individual program, the execution of those programs would involve a sequence of an instruction that will happen within the given program. We could look into the behavior of both the processor and the process, where we would like to monitor a process state or a process behavior by listing the sequence of instructions that execute for that process. Such list is referred to a trace. So you need the process control block, you do need the data associated with the process, you do need the program counter, and the program code, of course, and also you do need the trace of a process. The trace of a process is just a list of all the sequence of instructions that you needed to execute a process. And we could actually categorize the behavior of the processor by showing how the traces of the various processes are interleaved. So what is a trace in terms of definition? If you'd like to define a trace of a process, is the list of all the instructions that have been executed to complete the entire execution of a process. So the trace is used to monitor not where the memory is located in, not where the process is located in the main memory. It's all about the behavior of a process. Why we need to trace the behavior of a process? Because we would like to provide direction for the operating system, in addition to the communication with the processor, to switch between processes to support multiple programming. That means we need to know what's the kind of behavior we do have of each process by just defining or list the set of instructions associated with such a process by defining the term trace. And at this point, if you would like to monitor the behavior of the processor, it's easy for you to just show the traces of the various processes that are interleaved. So when we do this by monitoring the behavior of the process or the behavior of a processor, it's all about how the processes will switch among each other in terms of the running time. So if we have multiple processes, so like if you start process A and then there is a switch where like there is a need to switch to another process, process B, and then there is a switch, and then I would like to execute part of a process C, and then there is a switch. So this is where my switch, I use it to switch between processes. And then I might go back and then execute another part of A, and then I do switch. So keep going. This switch that I use it to transfer between or to switch between processes is called dispatcher. So this piece is the dispatcher, which is just a small program which is responsible of switching between processes. That means the dispatcher is directly connected to the processor because it gives directions to the processor to which process the processor would need to execute. The decision of which process to be scheduled, which process should be executed is not done by the processor. This is done by the operating system, in particularly the process manager component. And we use the dispatcher as a small program, like a couple of instructions that we will load it in the main memory every time we would like to switch it between a process to another process. Let me give you an example where we could actually see the importance of monitoring the execution of processes by observing the interleaving of their execution and where they are located in the main memory, how the traces will be different, how the processor will switch between one process to another process. If we look to this figure, we can see that we have the memory layout of three processes: process A and process B and process C. Process A starting address is 5,000. Process B starting address is 8,000. Process C starting address in the main memory is 12,000. The dispatcher is a simple program located in the main memory from a starting address 100. So to simplify the discussion, we assume that we are only dealing with main memory. There's no virtual memory. So if we have a virtual memory, the story might be a little bit different. But for this example in particular, I would like to show you the execution of processes and how the processor will actually switch between processes by monitoring the trace of the process and the interleaving traces of all the processes. So all the in this figure, all the three processes are represented by programs. So we do have programs that would need to be executed, and they are fully loaded in the memory. And again, we can see the dispatcher, which is the small program I was referring to that is responsible for switching the processor from one process to another. So now we know the starting address of each process, and we know also that the program counter will contain the address of the next instruction to be executed. So now we can see the memory, but we would like to know how the switching between those processes will take place, and by using the traces of each process. So if we just list the sequence of instructions for process A, it just started from location or address 5,000 in the main memory, and then only 12 instructions are needed to execute process A, where the starting address is just 5,000. While for process B, the starting address is, so this is for A, this is for B. The starting address for process B is 8,000, and it only consumes 4 instructions. Sometimes we use the word instructions, sometimes we say 4 cycles. And then the last one, which is the trace of process C, it shows the starting address of process C, 12,000, and the process C is completed if we consume 12 cycles or 12 instructions. So these are the 3 traces of each process. So the first 12 instructions will be executed for process A, and then another 4 instructions for process B. And then for this example in particular, we assume that's like assumption, so I can show you how the interleaving between the processes will take place, that process B executes 4 instructions, and then we assume that the fourth instruction, like this, the instruction in at this address, will actually invoke an input-output operation for which the process, in particular process B, must wait. That's why we have limited only 4 instructions for process B. So the process will wait. Now what would happen? Like, which process will be resumed next? That will define the behavior of the process as well as a behavior of the processor. Now, by using the information about the traces as well as the starting and ending address of each process, let's see when we combine the traces of all of those processes, what would be the processor point of view? If we look to this figure, we can see that there we have interleaved traces that will run, that will result from running the entire 52 instructions or cycles. So in total to execute or run the 3 processes. So if I want to run process A and process B and process C in a multi-programming environment, I do need a total of 52 instructions. Let me show you how this 52 is calculated. First, the shaded area in the graph, so this one and this one, in addition to this one and this one, it just by listing the starting address and end address of those sequence of instructions that will be executed as a dispatcher. So this is the dispatcher code, and we will have to load it into the main memory every time we would like to switch between a process and another process. So this is the code for the dispatcher. It's stored once in the main memory, but we will reference, like we have to reference this address to call the dispatcher, so we could switch between processes. We know that the same set of instructions is executed by the dispatcher in each instance because it just performs the same functionality, which is just executing the dispatcher. In this figure in particular, we assume that the operating system only allows a process to continue for execution for a maximum of 6 instructions. That's just for assumption. The main reason why we do have this assumption is we would like to see the switching between the processes. Like, we don't want to run a process at once, like the entire process at once. We would like to monitor the behavior of the processes when there is a need for switching between the processes. So after 6 instructions, this is like this is an example. It's not mandatory that after 6 instructions we will interrupt the process. No, just like an assumption made. So we could see the importance of traces and the importance of the dispatcher in monitoring the behavior of a process and a processor. So in this figure, the first 6 instructions, so in this figure in particular, we know that the first 6 instructions of process A would be executed because we only allow 6 cycles. That's the max limit we allowed for this example. So we have to interrupt the process A and then get the code or the sequence of instruction of the dispatchers to be involved. And then we will move to process B. This is the start address and the address of process B. And then we call the dispatcher again. And then we will call process C. And because we do have a limitation of 6 instructions, that means we have to interrupt the process. Keep in mind that process B will call, as in this example, an input-output instruction. That means the process B will have to wait like until the input-output request has been satisfied or has been performed, at which we could resume process B. So at this moment, the processor will only alternate between A and C until process B receives a response for the input-output request that has been made. So once we move back, we have executed the 6 instructions of additional of the process C. So now we are at cycle 28. We do need another 6, like the entire code for the dispatcher, which we assume is just like 6 for now, because we do have this limitation as well. And then we're going to resume process A. So we have to go back and resume A again, because there is no need to block A, because A is ready now for execution. It was just interrupted because we only assume maximum of 6 instructions for execution. And now we are at cycle 40. We have another 6 instructions for the dispatchers. And then finally, we ended up with the code for process C. So now we complete process C. And after that, process A and B are completed, and process B is still in a waiting state. This graph or figure shows the interleaving between the processes, the behavior of the processes, which I said when we refer to behavior of a processes means the set of instructions to be executed for each process. And then also the behavior of the processor. How the processor will switch between process A and process B and process C, that's part of the operating system. As I said before, the operating system is a manager of a general manager of forming main components. One of those components is the process manager. The process manager, as a part of the kernel, is responsible of identifying the traces of each process. It's responsible of calling the dispatcher to switch between the processes, and it's responsible of scheduling which process will be executed next. Like, for example, in this graph, we started, or in this figure, we started by A. Let me change the color, which we started by process A, and then process B. I could easily like continue process A here, but because we do have a queuing model to represent the lineup of the processes, which will be determined based on the scheduling mechanism of the operating system, we switch to process B. So how this done? Based on describing the behavior of the processes, as well as the behavior of the processor, based on the dispatcher and the scheduler. So after we identify the process state and the processor state, we know that the operating system principal responsibility is to control the execution of the processes, which means we need to determine the interleaving pattern for execution and allocation of resources to each process. The first step when you decide to design an operating system your own is to control the processes, which means we have to describe the behavior that we would like those processes to exhibit. We could construct the simple possible model by observing such behavior of the processes by monitoring the state of each process. So the simple model that we could use it to describe such behavior of the processes and then identify the traces of each process. And this will help in determining which process should be scheduled for running or not, or execution. The simple model, we call it a two-state process model. So we could observe at any time that a process is either being executed by the processor, so we refer to it as a running state, like the process is in a running state, or the process is not a running state. So if the process is in execution by the processor, we call it a running state. If the process is not in execution by the processor, then the behavior of such process is simply not a running state. So in this model, we only have two states of a process. A process could be like, sometimes we use a simple scenario to describe it. So this is a not running state. And then we do have a running state when the dispatcher decided on the process to be executed. So the process would move from a not running state to a running state. So when the dispatch decided that this process would be executed now, so the process will move from the non-running state to the running state. And if the process is completed, then the process will exit the system. And of course, a process once entered the system, immediately the process will be identified as a non-running state. If there is a need, or at some point there's an interruption to the process while the processor was actually running the process, then we say the process has been interrupted. So we say interrupt, or sometimes we call it pause, and then the process state will move back from running into not running. So you have to keep in mind that when the operating system creates a new process, so as I said before, we create immediately a process control block. So when the process is created by the operating system, so the process control block is immediately created for the process. And then the process, if it's ready for execution, it's not executed yet, it's ready for execution, then the process control block will be loaded into the main memory. And then the process will enter the system as a not running state. And then the process will exit the system if it's completed, as I said. Otherwise, if the process is interrupted while the process is running, then the process will go back into a non-running state, and then back and forth until the process leaves the system. So this is a very simple state diagram to describe a behavior of a process, because not necessarily that if we have a process, that the process could be on a running or not running state. So keep in mind that this is just a simple model. Later on, we will add more complexity to the model. But if you would like to monitor the behavior of the processes and how the processes switches between a running and not running state, the basic model is the two-state process model. So in terms of queuing theory, because keep in mind that when a process enters the system, the process joins a queue. So assume this is process 1, and then process 2, process 3, and 4 for assumption. And then process 1 immediately will go into a not running state. The dispatcher will decide that process 1 is ready for execution. So initially process 1 was for not running state, and then process 1 will go into a running state, and it might leave, assume process 1 just left the system, so we're done. And then process 1 is not in the queue anymore. So the next one to be dispatched will be process 2. Process 2 entered the system as not running. So this is the second cycle. Process 2 will be not running state. And then the dispatcher has decided that it's ready for execution. So process 2 will be now a running state. And then process 2 is interrupted. This is assumption made. So process 2 has left the queue originally because it was called by the dispatcher, but because it was interrupted, it goes back at the end of the queue again. So now process 2 again. So this is a queue model where processes will have to wait in a lineup before a dispatcher will decide to call or to retrieve one of those processes to be executed. So if we look to the queuing diagram, so you have the queuing diagram right now that would describe the queuing behavior of the arrival of processes and the processing of those processes at the processor level and then leaving the system. This is the simple queue model that you could look at. We could begin with the design of those elements of a process once a process is created. And then the process control block of each process will be created. And then each process would be identified by its own process control block. So this is the processes. Each process has a process control block that is actually stored in the queue as well. So there must be some information that is related to each process. So we could keep tracking of the processes addresses, the starting point and point. That's why I said we store the process control block inside the queue. include the information in the process control block for each process, including the current state of the process, the location in the memory. This is where we need the process control block for. Processes that are not in a running state, we know that they must be kept in a sort of a queue, like first come, first serve, or first come, first leave. And then they have to wait for their turn to be executed. This is the single queue. So now this system, which is aligned with the two, so this system aligned with the two state process model. So with the two state process model, this is the corresponding queue diagram, in which we only have one single queue. So just have one single queue. Processes would leave the queue if the dispatcher decided that now the process should be executed by the processor. The process will be allocated to the processor for execution. So the first phase is waiting. So the process has to wait a little bit before the process is executed. So the waiting here, I always refer to it the non-running state, and the execution is the running state. So each entry of the queue is a pointer to the process control block. So when I say the process control block is stored in the queue, like in our memory management, we say that each entry in the queue is simple pointer to the process control block. Alternatively, you could have just like a simple list to design your queue, or you could have a linked list, like a little bit familiar with data structures. So you could have a linked list of data blocks in which we guarantee that each block would represent one process. And it's more flexible to implement a queue using linked list as compared to representing a queue as just like one array. So using this queuing diagram, we could describe the behavior of the dispatcher in terms of which process is now scheduled for execution. When a process is interrupted, so the process will transfer back to the queue and then will join the waiting processes, and the process has to wait for its own turn. And because we use a queue system, so it's first come, first serve. So if the process has arrived first, it would be executed first. If the process has arrived last, it will be executed last, unless we have a priority queue. So if we do have a priority queue, we are giving priorities for processes. So processes with the highest priority will be executed first. So once a process leaves the system, the dispatcher will immediately recall one of the processes in the queue for execution. If the process is already in running state and there is an interruption, the process will go into the queue again. So now I would like to go over some quantitative analysis about how to assess the performance of the scheduling system provided by the operating system if you do have a one single queue. As I said, a queue is a first come, first serve model, but the scheduling mechanism might be first come, first serve, or it might be highest priority first, or it might be shortest time first, like the shortest job first. There are different options that the operating system could decide on which scheduling mechanism is needed based on quantitative measures that we could retrieve to identify the performance of a given scheduling mechanism. Let me share with you this example. We will do the calculations of some quantitative performance measures and then compare different mechanisms and see which one is a good option for the operating system, giving in fact those processes. So in this example, we do have 5 processes. So in this example, I have 5 processes. I do have the arrival time of each process. So I know on the clock at what time each process has arrived. And I also know the processing time or the burst time, how long each process has been assigned to the processor, how long it took while it is processed by the processor. So let's now create a new blank page so I could actually go over this example with you in details.